A very good afternoon. Today we are going to see about some characteristics of steam power generating units. So if you see the steam power generating units, this is a simple block diagram of boiler turbine generating unit, whereas we are applying enormous amount of heat, that is via our furnace to the boiler. So that boiler steam will be produced. Superheated steam will be produced. That will be hitting the turbine. So what is the temperature here in the boiler is approximately around 600 degrees Celsius to maximum of 1000 degrees Celsius. They may gone up to, depends on the type of the generating units and the size of the generating unit. And here, if you see, like in the boiler, enormous amount of like heat is given to the boiler, so that superheated steam is given, is hitting this turbine. So that is coupled with a generator. So that generator is connected to a common bus or auxiliary power system. This is the simple block diagram of boiler turbine generating unit. And if you see the characteristics, so this is the input-output curve of a steam turbine generator. So if you see, like in the x-axis, we have taken the input as the heat, that is MBTU per hour, or the fuel cost in dollar per hour. Okay, so generally, and in the British general US market, we are going for like foreign market, we are going for dollars, and in Indian market, if you say like that is rupees per hour. So you can also write it as rupees per hour. That is not at all a problem. So what here we have taken is, so this is British thermal unit. Okay, so million British thermal unit, like dollar per hour. That is taken in the. So if you take either heat or fuel in the x-axis, so here in this axis, this is y-axis. In this x-axis, what we are taking is the power generated. We are taking it as in the x-axis. That is the power output. That is in megawatt. So we are mentioning in the megawatt, that is 10 to the power of 6. We are not mentioning in the kilowatt or watt, because power generation generally, if you take like all the power generation, it will be in the megawatt, whether it may be of 100 megawatt, whether it may be of 1500 megawatt, 2000, 2500. So if you take like thermal generating units, so minimum 1000 megawatt to the maximum of 4,500 megawatt. So it depends on the series of the stations. So one station, one generator is of 1000 megawatt, like that, 1000 into 4 or 1000 into 2, or otherwise 500 into 2, like that. It depends on the size of the generators. And if you see, like with the increase in the heat rate, automatically the power generation also increasing. If you see this diagram, so whatever the heat we are giving, so if the heat given is less now, the power generation also will be less, because the steam produced in the particular this boiler will be reduced automatically. The pressure that is hitting the turbine also will be reduced automatically. Your generator also will be generating less. Meanwhile, if you increase the heat here, if you increase the heat over here, so more heat is directly proportional to power generation. That we have already seen that relationship and all. So just this is about the characteristics. So here, if you see the increase in the heat leads to the increase in the power raise. Okay, so gradually it is increasing like this. And also it also depends on the fuel rate, same like that. So whatever the rupees we are going to spend, whatever the rupees or dollar amount we are going to spend over here, that will gives the more amount of power. So lesser the fuel cost, lesser the power generation. Okay. So if I'm just burning only 1 ton of coal. Okay. I'm getting only around 1 megawatt like that. So if I'm burning 2000 megawatt, sorry, 2000 tons of coal like that, I'll be getting further more. That is 2000 megawatt or 4000 megawatt I will be getting. So like that, here also with the increase in the fuel rate, the power generation also will be increasing to the maximum, to the minimum, to the maximum. There is some limits for a particular generator. If you take a generator in a particular generating station, there will be some minimum generation, even though say for example 100 megawatt generators we are taking. So there is some in nameplate. If you go and see the nameplate, you can also run it for very low generation also, but efficiency will be losing. So generally there will be some limit. So minimum some 80 megawatt to the maximum of 105 megawatt like that. Okay, if you exceed 100 megawatt to more than that, that is more than 105. Okay, again the thing is that your the winding inside the alternator also will be affected, and also lifetime of the generation also will be affected. So there is some limit. So minimum power generation is, say for example here it is 80 megawatt. So maximum generation 105 megawatt or 100 megawatt like that. So depends on the fuel spent. Meanwhile, the power generation also increasing gradually. So this is of input output curve of a steam turbine generators. That is, so H is in billion thermal units per hour. Okay, per hour heat input to the unit, and F means fuel cost. Fuel cost, or H is nothing but heat rate. Heat rate that is input to the unit for the fuel. So next, if you see the next curve, yeah. So this is the incremental heat rate characteristics. Incremental heat rate characteristics. So here, what we are, yeah. Here in the y-axis, what we are taking is incremental heat rate. Incremental heat rate in the sense with like change in heat with respect to power. Okay, so we are doing the first derivative. The first derivative. So what we are doing is we are taking the incremental. We are taking the differentiation with respect to power. Okay, so that is called incremental heat rate. So here what we are doing is in the y-axis we are taking incremental heat rate, that is del H divided by del P BTU per kilowatt hour. Here same like that, incremental fuel cost del F divided by del P dollar per kilowatt hour. So here also we are taking power output in megawatt. With the increase in incremental heat rate, automatically the power generation also will be increasing gradually. Same even though with the change in heat rate also, leads to change in the with the gradually increase in the heat rate, automatically power generation also increasing like this. So this is the minimum power generation, maximum power generation. Sometimes we are in the limit itself. The problem we are solved now. The limit itself, they will be giving some, you should not exceed based on the generator size. So 500 megawatt. In the limit itself, what they will tell is you should not go less than, that is 475 megawatt. You should not go beyond 510 megawatt. Like that, some limits will be given. So minimum and maximum power operating limits. So that the generation, if the generator, if it is operating between that particular limits, then it will be it will be good, and also the efficiency also will be good. Okay, so if you are overloading the generator, if you are overloading the generator, 500 megawatt generator to 700 megawatt overloading, so definitely your lifetime of the generator will be increasing, and also your efficiency also will be somewhat decreasing. Okay, due to the heat generated in that particular generator. So that is also there. So that also you have to take it into the account, because we have solved some problems also based on this. That is minimum and maximum operating limits. Next. Next, net heat rate characteristics. Net heat rate characteristics of a steam turbine units. So if you take the net heat rate, so here what we are taking is unit heat rate curve, that is H bar P, that is BTU per kilowatt hour. So net heat rate, if you say net heat rate, that might be of like a heat rate might be of somewhat 1000 degrees Celsius we are starting. So maximum heat generated in that particular boiler is 1000 degrees Celsius. That is in it is here, it is mentioned as like a British thermal units per kilowatt hour. So British thermal units per kilowatt hour. So maximum it is 1000. Okay, so it will be gradually if you see, like gradually it will be decreasing and again it will be gradually increasing. So that is the net heat rate characteristics of the steam turbine generating unit. Yeah, so this is approximate representation of a heat incremental heat curve. So incremental heat rate is del P del H divided by del P. So BT. So approximate representation of an incremental heat rate curve. So it will be like gradually like it will be increasing like this. So gradually increasing like this, again gradually increasing, again gradually increasing. So it will be like as a curve is like zigzag. So what we are doing is for making it somewhat linear. So we are making we are considering that to somewhat linear. So this is the actual thing. So this is the approximation what we are doing. So actual thing it will be, if you see like, so it will be gradually increasing. So net heat rate curve gradually increasing with respect to power. So again it will be increasing like this. So what we are doing is we are making that non-linearity to linear. So we are making that is non-linear curve to, we are considering that to linear, and we are going to solve the problem. So but practically it is a non-linear problem. It will be increasing or decreasing with respect to the output power. So here yeah, here if you see like variations in the steam turbine units. Okay, so this is the characteristics of steam turbine units with 4 steam valves. 4 steam valves. So generally from the boiler, superheated steam is being generated, and it will be traveling over some long distance, because your boiler is somewhat far away from your generator. Some 100 to 200 meters it will be far away from your generators. So by the time that steam is carried by a steel valves. Okay, steel valves, stainless steel valves. Okay, if you see like in the thermal power station, you will be seeing that valves. that valve. So generally that valve will be opening. Generally there will be some 3 or 4 valves to the different turbines. And sometimes if you see that valves also will be opening and closing. So this is the steam admission valve, different steam admission valve. This is the first steam admission valve, second valve, third valve, fourth valve, like that. So it will be first valve will be somewhat opened partially. Another valve will be opened somewhat more than that. Another valve will be opened fully, like that. But generally, practically, if you see, due to the demand, due to the power demand, because this generator, what we are generating, is directly coupled with the bus, no, in the bus system. So in the bus, that is bus means bus only. Our load, that is demand, will be connected. Our loads and all will be connected. So suddenly there will be the rise in the power demand. By that case, what happens is the valve will be opened fully. So sometimes there will be no load will be very less in the winter season. If you see, load will be very less, whatever we forecasted, but the load will be less. By that case, what happens is automatically the power generation also, that valve also will be closed partially. So that is called a valve point loading effect. Okay, valve point loading effect. But I'm saying it will be closing like this and opening like this. But imagine if you are standing in the load dispatch center. By in that scenario, your valve will be opening and closing like anything, like very fast, because it will be directly coupled. That feedback will be directly taken with, from the the bus, external bus. So in the bus, if you see, by minute, the load will be increasing or decreasing. Sometimes this at 12 o'clock time. 12 o'clock time now, the weather is very hot outside. So what everyone will do is, after sometimes they will simply on the air conditioners, ACs, air coolers, like that. So simply load will be increasing. Sometimes after cooling, after 2 o'clock, suddenly what they will do is they will simply off after 2 hours. What they will do is they will simply off the air conditioner. Suddenly it will be dropping. Suddenly some industrial loads in this time, like at 12:30 to 1:30 or 2 o'clock, will be the industrial break. So if you are working in industries, there will be some 1 hour break or 1.5 hours break. So in that time, the load will be of very less. They will generally switch off all the machineries in that scenario. So by that time, whereas in the domestic loads, we will be using more appliances like ACs in the summer season. So the load will be more at the domestic side. So after 2 o'clock, 3 o'clock, what they will do is we'll simply off our ACs, we'll switch on our fan or something like that, because generally people will be using the optimally using our electricity in home also. What they will use is, after 2 hours, the room will be very cool. So what we'll do is we'll simply switch off, or automatically that inverter itself will be switching off that particular air conditioner for some times, like that. So suddenly the load will be dropping and increasing like anything. So by that time, if you see minute by minute, second by second, it will be vary. So if say for example, if it is directly, that feedback is directly coupled with the that valves. So this valves, what it will do is it will open and close. It will open and close like this. It will open and close. So if it is open and closing like this, if you draw that particular graph, it will be varying like anything. It will be varying slightly. It will be going high. Sometimes it will be going low. Sometimes it will going like this. So like this, okay. So it will be like a zigzag. It will become. So this problem is very difficult to solve, because whatever the problem we are solving in the notebook, in the class, how we are solving is we are just considering how we are considering fuel cost characteristics. Just like that, fuel cost characteristics of unit number 1, 2, 3, F1, F2, and F3. That is some 560 plus 0.0048 plus P1 square plus somewhat 4.2 P1. Like that we are taking. Like that we are taking. So that is of constant. The fuel cost coefficients of constant value, and also generator limits also some constant limits we are taking. So 500 megawatt generator first generator should be 500 megawatt. It should be within 450 to 550 or 600 megawatt. Like that, that will be some constant. So for 3 generating units, solving that 3 generating units is very simple. Like it will take some half an hour of time so that we can easily solve that particular problem. That is very simple. But imagine in the so if you see the this practical this curve, it will be varying like anything. It will be not varying linearly. What we have shown previously, no? Previously we have shown only linear curve. So that will be not. That is somewhat ideal case. Somewhat ideal case. Practically, as you are seeing here, it will be varying like anything. It will be varying and decreasing like that. It will be keep on varying, decreasing, increasing like that. So by that case, if you solve that problem, if you solve that particular problem, it will be the very difficult thing to solve. So that's why what we are even in power system operation control, even in your advanced power system analysis. So in some of the power system subject, what we are doing is we are considering something, considering that as linear, so considering the non-linear as linear, and we are solving the problem. And what we are doing is we are assuming this load will not be varying. So while solving unit commitment problem, will come to know. What we are doing is in optimal power flow and Newton-Raphson method, Gauss-Seidel method, what we are doing is we are making that as a flat start. We are starting from the flat start. That is we are starting from 1 per unit. 1 per unit. Full generation is being given to the particular sending end, and like that we are calculating. Like that we are making some consideration, and we are making some assumptions in while solving the Newton-Raphson method. Even in power system operation control also, what we are solving in the class in the problem is somewhat only one at a particular time it was taken. Maybe at peak time it was taken, that fuel cost characteristics. So and also generation also, like approximation, we are going for approximation. That value we are solving, and we are trying to find out so how the dispatch the power dispatch will be. So this so based on the fuel cost characteristics, how the power generation will be happening from the first generating unit, how the power generation will be happening from the second generating unit, third generating unit. Like that we are calculating, but practically it will be not the say. So that's what I want to say here. So this is the like characteristics of steam turbine generating units with 4 steam admission valves. So this is the parallel steam admission valves. That is 4 steam valves. 4 steam valves is connected, being separated to a particular like one turbine or many turbines. So in that turbines, how the generation will be, like that we have seen. So another thing also I said no. So valve point loading effect. That is one of the important thing you have to understand. Valve point loading effect. So this I think this we have seen in the class itself. Common figure steam power plant unit. There is gas turbine operating units. Same like steam turbine units. Next, we are moving on to our hydro. Yeah. So if you see like hydroelectric unit. So yeah, input is in Q. That is discharge of the water. That is acre feet per hour. Acre feet per hour. That is the unit of discharge. Acre feet per hour. So if you see like here in the x-axis, it is output. That is in the power. Power is in megawatt. Okay. So with respect to the change in the discharge, with respect to discharge, automatically the power generation also will be increasing. If the discharge is like less, the power generation also less. The discharge is more. So as I already said, from the penstock, the water is sitting to the turbine. So what is the pressure inside that turbine is from the velocity from the 120 kilometer per hour to maximum of 150 kilometer per hour. That is the maximum speed of a train. So in that much speed, that water is hitting that turbine. So due to the discharge, that is the discharge. So discharge here, what we are assumed is acre feet per hour. Acre feet per hour. So that much discharge, it is hitting the turbine. So that much velocity, that much speed, that is being hit to that particular turbine. So that the power generation also will be maximum. Like this is the example given for net 400 feet. So 400 net head is 400 feet. This is being generated. So 400 feet. Like normally our dam capacity will be at 120 feet, 150 feet like that. But here this is of US United States. Their dam is of 400 feet. So the net head is 400 feet. So that power generation also will be like maximum. So in our like a generating station, so maximum we are generating around 100 megawatt. So 100 megawatt, but that generating unit may be of 5. So 100 into 5, 100 into 10, or 200 into 5, like that. So maximum 1,000 megawatt or 2,000 megawatt. It depends on the water capacity, what we are having, how much feet we are having, how much acre we are having, like that. So 150 feet and how much acre. So this much acre we are having. So that much power generation it might be for our Indian system. This is the hydroelectric unit output, input. Okay. Next we are seeing hydroelectric unit. Hydroelectric unit. I think you already studied this in power system 1. So that's why I'm not touching more on that. So if you see like incremental water heat curve for hydroelectric, incremental water, that is dq divided by dp, acre feet per kilowatt hour. So if we take like incremental water heat rate curve, so first initially it will be somewhat gradually for sometimes, and slowly it might be increasing. Slowly it might be increasing like anything. So with respect to say for example, the discharge might be of as I said, no discharge might be of this much acre feet per hour. So gradually it will be generating because penstock once it what in the like valve house, one valve house will be there. So there only this that penstock discharge will be maintained. So sometimes if you want to generate more power in the summer season, generally we will be opening that penstock that valve fully. So discharge might be of maximum. So sometimes in the winter season, whereas load will be somewhat less. In that scenario, what we are doing is we are just partially we are open. We are opening for like 3/4 of the valve, so that the discharge might be of somewhat lesser than the expected level. So in that scenario, it will be of lesser. So by that time, there will be a call from load dispatch center. So suddenly there is a demand. So that what we are doing is in the steam valve, in the steam house, valve house, what we are doing is we are opening the valve fully. So the maximum discharge is being heated. So the generation also will be of maximum. So like that, gradually, generally it will be discharged. Like this is the incremental water heat rate characteristic. No? So generally it will be gradually. So it will be increasing like in a sudden spike. Sudden spike, it will be increasing. Okay. So next, if you take like input output curves for hydroelectric plant for variable head. So this is already we have seen for 400 feet. So if the discharge is being increased, that is for 450 feet. So 450 feet means so the power generation also will be increasing. Again for 500 feet, 495 feet, like that power generation will be of maximum. Like that, this is the input output curve for different variable heads. This is of variable heads of dam. Yeah. So here, if you, what we are seeing here is pumped hydro storage plant. So pumped hydro storage plant concept is like in the non-peak hours. Non-peak hours means say for industrial, the peak hour is like the morning 10 o'clock or 9 o'clock to like afternoon 1 o'clock. That is the peak time for industrial. And non-peak hours means for industrial and domestic as well as domestic. Non-peak hours is this like 11, 12 to 1 or 2 o'clock. So in this non-peak hours, what they will do is, and also night time also non-peak hours, non-peak for your domestic and as well as industries, that will be the peak hour. So whenever that will be finding non-peak hours, what they will do is, as I already said, dam will be of stage by stage. Stage by stage. What they will do is, the first stage, the water will be get open. So in the first stage, they will be generating around 1000 megawatt. So thereby the water is flowing for another some 5 kilometers or 10 kilometers, and there you will be finding second stage. Second stage will be generating around instead of 1000 megawatt, will be generating around even 500 megawatt. So again, the 500 megawatt is being generated. Again, it will be passing over some 20 kilometers or 30 kilometers. Again, stage. Third stage, again we are utilizing that water. Again, we are utilizing that water. But like a generating station might be of same size. Maybe this whatever the water, maybe sometimes like the water will be flowing into the canals or dams. No? Sometimes it will be taken for the irrigation purpose. That way, the water pressure is decreasing in the second stage. So that's why we are decreasing the amount of power generation in the second stage as well as third stage. Third stage might be of somewhat mini hydro power station of 10 megawatt or 25 megawatt, 50 megawatt, like that. We are generating. So In the non-peak hours, what we are doing is we are taking that water, okay, back to the dam itself, back to the dam itself. So what it will do is it will also same turbine will be acting as a motoring action. So like the penstock will be there. So imagine this is the penstock. So the penstock will be there. So here the turbine will be there. So after the turbine that is being coupled with the generator, after it will be hitting the turbine, that water is going outside to the dam, the second stage of the dam. So in that scenario, so what we are doing is we are taking same water in the same canal itself. In that scenario, this turbine will be acting like a motoring action. So the same alternator will be acting as a motor. So what we are just sucking all the waters, not all the waters. We are sucking maximum water that is being sent to the second stage, to the particular first stage itself. So we are storing the water. So why we are storing the water in the summer seasons? You know, the water is very scarcity nowadays because no rainfall, and also only we are depending on the hilly regions. So say hilly regions, water is being generated slowly. It is collecting from all the tributaries, and it is being stored in the dam. So nowadays, due to the hot sun outside, so no rainfall also. So we have to optimally use our water resources also. So simply like that, if you just generate that water, just generate the power from the water, and simply like that we are letting out now, it will travel to some other distance, and again it will go to the seas, and it will simply go to the seas without store. So what, and some agriculture also they are using. So what, for power generation, where we will get the water? So what we are doing is, in non-peak hours, we are pumping that water to the the first stage itself, and we are utilizing that water for again the power generation. But even for pumping the water, we have to use a huge amount of power. That is 70% of say for example 100 megawatt we are generating in that particular power plant. So you need to spend around simply 60 to 70 megawatt for pumping that water, because huge amount of, because your first stage of dam will be of some 1 kilometer or 2 kilometers far from your generating station. So that much pressure you have to give to that water, so that it will be stored. So normally in our house itself, for pumping from 20, 40 feet or 50 feet itself, we are using 3 HP motor, 2 HP motor. Okay, sometimes 1 HP motor also you'll be using. So in the apartment type, what will be, they are going for like 3 HP motors, 5 HP motors, because apartment five storage buildings will be there, then 10 storage building will be there. So in that scenario, you need to go for very high HP motors, 10 HP motors, 5 HP motors, like that in the apartment type. So that much pressure you need to give to take suck that water to that particular your overhead tanks. Imagine same like that. So you have to carry that whole water, not only whole water, like approximately 60 to 70% of water, that you have to take that to first stage. So you need more amount of power. So that is 60 to 70% of power what we are generating, that might be utilizing for pumping the water to the first stage, so that you can use. So that is also there. So you have to spend some power also for pumping. Pumping needs more mechanical energy. So and also that is directly proportional to electricity also. So you need to spend more on that particular thing, so that water is being pumped to that first stage. So if you see, like, this is the input output. So this characteristics you already know. So pumping also, what we are doing is we are doing the pumping like this in this same thing. So the pumping characteristics might be of same. So whatever the generation we are doing, approximately 50 to 60% we have to utilize the power from the generating. Say for 100 megawatt we are generating, we have to minimum use 50 megawatt to pump that water so that it will be reaching the first stage. So that also there. So in non-peak hours, you can do that. If the generation is more, like demand is less, in that scenario, you can go for the pumped hydro storage power plant.